Transformers are devices that step up or step down voltage. And if we take a look at this diagram, it actually shows us a transformer. What we have is a core that is built out of laminated iron layers generally, and that's to produce any what's called eddy current losses in it, and it transmits the magnetic flux from one current carrying coil to another current carrying coil. The one where the power comes in is said to be your primary, and when the power comes out is called the secondary. Now I say power comes out, but these are insulated wires, so it's not current flowing through this thing that's actually making that happen. This is an alternating current, so as this current comes in, it's producing a magnetic field that's first changing. It's getting stronger in one direction and then stronger in the other direction. Stronger in one direction, stronger in the other direction. And that changing magnetic field is going to move through this coil of wire, and it's going to cause an induced current over here. And so transformers are used to change the voltage of something. So we can have 10,000 volt transmission lines, 100,000 volt transmission lines that carry alternating current power from the power plant to substations, and then it can be stepped down to a much lower voltage for us to use it. So these are all based on Faraday's law of induction and that changing magnetic field. There's actually an equation that will show us how to calculate the current produced from a generator, the voltage from a transformer, or the voltage in a transformer. It is important to notice they only work for alternating current, because if this is direct current, then this creates a constant magnetic field and nothing changes, so we're not going to have any flux, and it's just an electromagnet at that point. Okay, so the transformer equations are pretty straightforward. Let's take a look. Alright, so what we had is the voltage of the source produces or is induced, sorry, this is not the source, the secondary coil's voltage, if we look at this in terms of electromagnetic induction, is given by the number of turns over on that side times the change in flux divided by the change in time. Oops, delta T. That tells us the induced voltage on the secondary turn, or on the secondary coil. Now, the primary coil is going to cause a magnetic flux, same equation. Whoops, phi not theta, divided by delta T. And all we have to do to figure out the voltage of the secondary compared to the voltage of the primary is divide those things, and most of this stuff goes away. They're in the same flux, so that's gone. It happens over the same time, so that's gone. So all I have is the ratio of the voltage of the secondary coil to the voltage of the primary coil is given by the number of turns on the secondary coil to the number of turns on the primary coil. Okay, so secondary and primary, that refers to which one we are thinking about. So usually this one is where the power comes in. That's our source. That's our primary side. Over here we get the power coming out. This is our secondary side. Alright, so this equation, pretty straightforward and simple to use. All you need to know is the number of turns around the transformer over here and the number of turns around the transformer over here, and you can figure out what the ratio of your voltages is going to be. Now, if you use Ohm's law, V equals IR, you can make a substitution, and you can see that the current in the secondary divided by the current in the primary is equal to the number of turns in the primary divided by the number of turns in the secondary, because IP VP has to equal IS VS. Now let's think about why that's true for a minute. Okay, this cannot create energy. So the rate at which energy is coming into this side is the rate at which energy is coming out of that side. Well, that's power, and power equals VI. Okay? So the total power on the primary side has to equal the total current or power on the secondary side, which means if we're stepping up voltage, so if our voltage goes up, then our current's going to go down. But if our voltage comes down, our current's going to go up. So these two equations show us that together energy is conserved, A step up transformer increases voltage, a step down transformer decreases voltage, but they do the opposite thing with current.